Hi everyone, I'm Nitesh. I'm a postdoc at the University of Illinois Urbana-Champaign, and the title of this presentation is High Fidelity Performance Analysis of Interdependent Infrastructure. Resilient infrastructure enable communities to be resilient. That's because infrastructure provide continuous flow of essential resources and services that support society. However, infrastructure are vulnerable to natural and anthropogenic hazards. And disaster preparedness is necessary to achieve resilient infrastructure in communities. Now, managing infrastructure requires large investments. However, uncertainty in hazard impacts and unavailability of accurate and realistic models impede the justification of large investments. Consequently, high fidelity performance analysis of interdependent infrastructure are required to plan for infrastructure and community. With this motivation, I'll start with a brief overview of infrastructure performance analysis. I'll then go into the details of infrastructure characterization, functionality assessment, and interdependence modeling, followed by an example, and then close with some concluding remarks. Time-varying performance analysis of interdependent infrastructure assesses the loss or reduction in reliability or functionality. Here we have three main tasks. First is to characterize the infrastructure, where we need to define the boundaries of the hazards and infrastructure systems and the resolution of the selected models. Second is to assess the functionality, under which we need to develop infrastructure models that can accurately represent their operational dynamics. And the third is to model the interdependencies, where we need to account for different interdependencies while allowing high fidelity flow analysis for each of the interacting infrastructure. However, there are challenges associated with each of these tasks. First, infrastructure are complex systems and their boundaries may exceed the region of immediate interest. Second, each infrastructure has their own operational dynamics and it is challenging to develop a consistent modeling. And third, it is conceptually and computationally challenging to perform coupled nonlinear functionality analysis to capture many types of interdependencies, more so if there are bilateral or looped interdependencies. We have made substantial contributions to address each of the three challenges. First, we provide guidelines for selecting the boundaries and resolutions. Second, we develop a mathematical formulation to model infrastructure as generalized network objects that can accommodate most operational dynamics. And third, we develop interface functions to decouple the functionality analysis of interdependent infrastructure. We start with infrastructure characterization. A region of interest may have multiple layers of structures and infrastructure, where each infrastructure system consists of many different elements. Characterization involves selecting the modeling footprints and resolutions for the hazard and each of the systems. Here, resolution includes spatial resolution, which captures the level of detail in the topology, and temporal resolution, which defines the frequency of the performance assessment. The hazard model and the different infrastructure models might have different footprints, and the definition of each footprint depends on several factors. For example, the type of information of interest, physical damage versus functionality, the location of strategic elements like generation nodes, as well as the interdependency. For spatial resolution, the number of elements modeled defines the corresponding tributary areas, which are the partitions of the region of interest served by individual elements. The definition of spatial resolution depends on data availability, type of performance analysis, interdependencies, and computational cost. Finally, the temporal resolution depends on several factors as well. A higher temporal variation in the state requires higher temporal resolution. For example, recovery modeling may require higher temporal resolution compared to gradual deterioration modeling. The type of solution approach for the performance analysis and the computational cost have a coupled effect, where depending on the computation cost for each run and the relation between the resolution and the convergence rate, there would exist an optimal temporal resolution for highest frequency. We now move on to generalized flow networks for infrastructure functionality. Once the boundaries and resolutions are decided, we model the infrastructure as a collection of network objects. For example, the mathematical model of potable water infrastructure may consist of two networks, structural and hydraulic flow. The state of each network is then defined by its topology and a set of capacity, demand, supply, and derived performance measures. The definition of networks is like that of components in structural reliability theory. Capacity measures are defined relative to the structural failure modes or functionality. Demand measures capture the occurrence of extreme events or regular service conditions, and supply measures capture the ability of networks to serve the demand placed on them. Once the network state is known, the next step is to assess how well the network is fulfilling the stakeholders' need. Performance measures such as network reliability and functionality can then be defined in terms of the capacity, demand, and supply. Moving on to interdependency modeling. In addition to performance assessment, we also identify and model the various types of interdependencies among infrastructure. We achieve this by developing an orthogonal classification of infrastructure interdependencies and then developing the mathematical formulations to efficiently model each class. We mathematically model the interdependencies using interface functions. Interface functions capture the combined effects of all supporting networks on the capacity measures and the combined effects of all supported networks on the demand measures. And then using the updated estimates for capacity and demand, we can update the network supply estimates as well as its reliability and functionality. We also provide the typical forms of interface functions that can account for various types of interdependencies. The interface function form can be built to replicate the effect of a known mechanism of interdependence, or we can use data to learn the interface functions. We can then graphically represent the dynamic of interdependent network objects as the following figure. Using this dynamic model, we can enable network-specific high-fidelity flow analysis while rigorously modeling interdependencies. And we can also model bilateral or looped interdependencies. Now let's look at an example. We use the proposed approach for modeling the interdependent infrastructure in Shelby County, Tennessee. Here we run a complete probabilistic analysis for a scenario earthquake of magnitude 7.7 occurring in the north of Shelby County. We modeled the potable water infrastructure serving Shelby County. The footprint of this water infrastructure model is self-contained within Shelby County, and it enables us to perform an accurate hydraulic flow analysis. We modeled the power infrastructure for a much larger footprint. We have a detailed model in Shelby County and a skeletonized model for the state of Tennessee, which enables us to perform an accurate power flow analysis. The model for the interdependent power and water infrastructure consists of four network layers. Equipment in both power and water infrastructure depends on the physical integrity of the structures supporting them, and in addition, the pumps have capacity dependence on the power infrastructure, and consequently, the power demand in the respective areas depend on whether the water pumps are functional or not. We then modeled the impact and recovery of this interdependent infrastructure, considering the actual recovery priorities. For instance, considering the power infrastructure, we can see that the confidence band for the functionality narrows over time because the initial damage states have high uncertainty and the functionality increases with the progress in recovery. Here, using the high fidelity power flow analysis, we can capture the spatial variability and the phenomena such as voltage collapse due to redistribution of loads. Results for the water infrastructure provide an insight into the effect of interdependencies with the power infrastructure. The first 2 days of power infrastructure recovery allow for the structurally accessible pumping stations to operate and significantly increase water infrastructure performance. The second substantial jump occurs around the end of the first week when most of the damaged pumps are expected. Finally, for some conclusions, we presented a formulation to characterize infrastructure, model its functionality, as well as the interdependencies. Using the high fidelity analysis, we were able to capture the spatial variability of the hazard impacts, as well as phenomena such as voltage collapse in power infrastructure and low pressure in water infrastructure. A benchmark example then illustrated the scalability of the proposed formulation in stochastic recovery modeling. We also observed that the interdependencies between the power and water infrastructure have a significant impact, especially in the first 2 days when rapid recovery of power infrastructure improved the performance of the water infrastructure. Thank you for listening, and if you have any questions, you can send them to me or Professor Gardoni using these emails.